Kan du säga något igen?
Ja, hör du det här? Testing. 1,
Ja,
2, 1, 2.
fantastiskt. Fantastiskt början. Du är perfekt i bild.
Ja, för här kommer alla stå ju snarare här.
Ja, jag måste stå där bak, men det är ungefär. Jag kommer ändå att köra en leveling.
Men om du typ aldrig är där, då det gör något.
Ja, just det.
Men om man står så här. Ja, det är jättebra.
Ja, det gjorde den här. Man hörde ju den där lite färre. Ja, precis. Precis, just det. Man måste hålla sista skottspärren. Precis, då håller man runt sin botten. Precis. Ja. Vad tror du?
Han sa att det var 20 stycken som lämnade sig bara på den här listan.
Jag skulle hellre kolla på vår presentation.
Jag också. Vad sa du?
Så att jag skulle hellre kolla på vår presentation än vad jag var.
Alltså. Jag skulle snarare kolla på om man bara har en sån här så skulle det gå på det och inte på det här. Hur skulle du förstå det? Kom du se vad? Du vill inte understand.
Jag hoppas vi klarar ett.
Vi ska ju köra imorgon också.
Nej.
Nej, det är idag. Alltid
Imorgon
idag.
kommer vi inte köra. Hon kommer att sätta bort allt tejp och markers och allt som kommer så här.
Ja.
Sminka.
Men vadå, imorgon ska vi inte köra.
Imorgon?
Nej, idag. Det är idag.
Det var tänkt att det skulle komma ett filmteam imorgon. Men det hinns inte med så att det blir efter helgerna. Så jag skulle gärna vilja att ni inte tog bort tejp och sånt här från golvet.
Så gärna.
Det vill ni ha det på.
Ja, tanken var, men det vi har att visa upp nu är ju typ ert system här. Så tanken var att köra det. Låta filmteamet filma det och göra lite intervjuer och sånt där.
Jag köpte ju en sladd.
Ja, du kan förhandla om priset.
Ja, det är lite allmänt om labbet och sånt där.
Nej,
så vi får se. Nu vet vi inte när det blir.
Sätta på något så kan jag se om man kan.
skärkläckar. Nej, det som är problemet.
Ja, det går bra, Lisa.
Det går ett rör, en T-koppling som jag ser ett rör med T-koppling till skeletter där. Till göra om det. Ja. Nej, T-kopplingen är helt, men röret är ju för koppling. Det drog jag av på den här.
Okay, so I think it's a 1:15 now, and there might be 1 or 2 more people coming, but I have sent double reminders, so this is the audience we have. Thank you for coming. We will see these exciting presentations about the project that these students here have been doing for the last 9 weeks. And after that we will go down to the lab and have a look there. So you're all very welcome down there as well. We will have some coffee and cake as well. And I don't know who will present here, but
We're waiting for Ari.
Yes. Okay, Ari.
Ari.
Yeah. He's back now. I was just introducing you. I didn't know you left.
Nervous. So.
Floor is yours.
Okay.
Okay, welcome to this presentation, final presentation of the Automatic Control Project course 2012. We are going to go first over some slides here in this room, and then we will move over to the SML, which is the Smart Mobility Lab, at around 3, and we'll see a demo of this system that we've spent the last 8 weeks building. But I'd like to ask the guys to come up here, and so I can introduce them one by one. So my name is Ari Hauksson, and I was involved with project management and miscellaneous processes, a little here and there. Bashar Mengana, he was responsible for trucks and T-modes, which is wireless communication. Kristina Westermark was in the quadricopter group. Fredrik Svensson was also in the quadricopter group. Jens Lykke, there on the end, he was working with the tower crane. Joachim Sundberg with trucks. Kai Imhäuser with tower crane, and Sebastian van der Hoof was.
Normally that doesn't happen, that people say my last name correct. So I'm always very excited when that happens.
So yeah, Sebastian was working with the motion capturing system that we use in the lab and miscellaneous processes, something in everything, pretty much. So I will call the guys on one by one when we go over the individual processes during the course of this presentation. But this is the overview of this lecture. I'm going to talk a little bit about the project management, how we have driven this project forward. Then I'm going to go into the final scenario that we are going to show later in the Smart Mobility Lab. Then we have wireless communication T-modes. That's a speak from Bashar. Motion capturing system, the thing that we use in the lab to position things in the room. That's Sebastian. Trucks are Joachim and Bashar. The crane and the quadricopter, these are the processes, 3 processes that we were regulating. The trucks, crane, and the quadricopter. And then we're going to end up with some conclusions at the end. So, Automatic Control Project course, what is that? That's this course that we 8 students are taking. It goes on in period 2 every year, and what we have to do is we have 8 weeks to implement a purchase order that I will show you briefly. The purchase order is what the teachers want us to implement with the overall system. So I can drag this over here. So we have specifications that pertain to the environment that we work in, the mocap system, which is the motion capturing, and the 3 individual processes, the trucks, quadricopters, and the tower crane. And then we were supposed to regulate all these together into an integrated scenario, which has a platoon of trucks traveling in a road network, being loaded and unloaded by the tower crane, and the quadricopter is supposed to hover over them while this is happening. So, the course started on the 22nd of October, and as I said earlier, it's 8 weeks. At the end of each week, we have to hand in a weekly individual report saying what we've done that week, and that's how the teachers know that we're actually doing something. Then we had a halftime presentation around the 7th of November, and then this final presentation on the 17th of December. And then there's also documentation, final report that we have to hand in. That's about 30 to 50 pages, and a documentation package which includes everything that we did with code and all the scripts and all that stuff, so that somebody else can resume the work later if need be. So yeah, you've already seen the purchase order. So yeah, the way that we did this, we decided early on after Joachim Liljeberg had a project management lecture for us, that we would do this in sprints, and we decided on weekly sprints. That's the agile way to run things through in sprints. So at the end of every week, we wanted to have a certain product implemented that we could say it's done for that week, and then we move on to the next part. And that went really well. It was a success, pretty much. We used Basecamp as online project collaboration software, and then we had a subversion document repository. And the way that this works, we have a product backlog, which is our translation of the purchase order that you saw in the beginning, and we work that into sprints every week. And we decide at the beginning of the week what we're going to implement in that week. So, software that we used, mostly LabVIEW, some MATLAB and Simulink for the modeling and identification. LabVIEW is like the controlling, we control everything through LabVIEW. And then Qualysys software, that's for the motion capturing system, and the little T-modes that we communicate wirelessly with the processes are running TinyOS. And then we have some Python scripts to do some neat stuff, like translation of the road system and such. Yeah, so the final scenario. We have signals going from 4 infrared motion capturing cameras to a computer. I could use this, yeah. So this is over network to a computer, which feeds this information to the computers that are controlling the processes.
Yeah.
Why does this?
The resolution.
Yeah.
Sorry?
The resolution.
Yeah.
Change the resolution.
I'm sure if I can do that. See if it works better now.
You need to keep them.
Keep changes on that.
Thanks. Yeah, that seems better.
Yeah.
Bit.
Somewhat.
A little bit. I don't think there's anything lower than this, so it's probably gonna be okay.
Close enough.
Close enough. So yeah, so we have individual computers running each of the processes. This is a very miniature picture of the tower crane. We have 3 trucks in our scenario, and then we have the quadrocopter, which is a 4-rotor helicopter. And these communicate through network between each other and to the processes. So this is basically over the wireless sensor nodes. So this is a picture of our floor. So we have 2 trucks here. These are the platoon. This is a 3rd truck meant as disturbance. And the only thing that this truck does, it goes around in a circle here, this blue path. And then we have a quadrocopter in the middle of this circle. And the tower crane has 2 loads that are situated within the range of the tower crane. So the first thing that happens in our scenario, where we are supposed to take the trucks to the loading dock, get them loaded, drive around, have them unloaded again, and then drive around 1 more circle and driving through the loading dock and go back to parking. And then the scenario is done. And the quadrocopter always needs to hover over the first truck in the platoon while it's en route. So the first thing that happens is the crane detects that there's a load here in its vicinity and sends a platoon request to this platoon. And designates one of them as the platoon master. That's the first truck in the platoon. And he sends a quadrocopter request to the quadrocopter asking for his services. And when the quadrocopter is at location, the quadrocopter answers with at location. And you can see the picture is staged. We put a cardboard box there. But you will see all this in action later. So now the trucks can drive a little ahead until they're outside the loading dock. So they stop around here and tell the quadrocopter, now you are going to have to go to rest. We don't need your service anymore. We're not driving in the road system. We're about to go into the loading dock. And it's very dangerous for the quadrocopter to go near this crane for obvious reasons. Hopefully you won't see that. So the next message is that the truck platoon master sends a message to the crane saying, I'm at location. The crane responds with go to waypoint, which is around here somewhere. so that I can load you with these goods that are in the vicinity, and the quadricopter goes to rest. So when the platoon is in location, they acknowledge that to the tower crane, and the tower crane puts this load here. You can see between the animations that there's a load here now, and the crane says go to waypoint to allow the next truck to get into the loading area. Then that one's loaded, and after that happens, the loading is complete, and in this message, loading complete, is the address information for where this platoon should take these loads to drop them off for unloading. So now the trucks are going to continue driving around in the road system, so they need the quadricopter, send a quad request. The quad responds when it's on location. You can see that it's a little bit in front and to the left of the first truck. This is deliberate because the motion capturing system would otherwise sometimes be shaded by the quadricopter, so the truck might get lost, not seen anymore. So the trucks travel around this circle, this outer circle here, and at this point they are designated as outside the unloading dock, and they send a no longer needed message to the quadricopter and an at location message to the freight hub, saying that they're outside. So the quadricopter goes to the helipad, and the crane sends a message, go to waypoint, which is around here, so I can unload you. And then the trucks acknowledge that by saying we're at location designated, and the crane takes the first load off and puts it down, and then tells them to go outside, tells the first truck to go outside so the next truck can go in. And when that's happened, then it can unload the second truck after this first truck has told it that everything is clear. So the second truck gets unloaded, and the first truck gets an unloading complete message from the tower crane, which means that they're going to be driving very soon on the road system. So they ask for the quad. The quad shows up, and you've seen all this before. Tells it when it's at location, and they had here one extra circle and then end up in parking, and that's when they don't need the quadricopter anymore because they're finished driving and they assume a parking position. And at this point the system is again at rest, except for this truck is still circling around. So yeah, that's basically what you're going to see in action later. So I hope that will explain a little bit better what you're seeing. And this happens all automatically, so we just press one button to start the system, and then this should go through the whole process once. So now we're going to hear Bashar talk a little bit about the wireless communication, the T-modes.
Yes. Okay, so I'm going to keep the presentation about these very brief. It's basically the one you see up there. So what we've done is we're using the code that is already on the KTH repository, so we haven't really modified that code, and it works well. So on the computer we use the LabVIEW application to send commands to the trucks or to the quadricopter. So what happens is that we have a serial forwarding server that takes the message from LabVIEW, forwards it to the T-mode. The T-mode then wirelessly sends the message to the T-mode on the truck or on the quadricopter. And then what happens is that the message is forwarded to the serial adapter and then forwarded to the polluter board, which gives a pulse with modulated signal to, for instance, with the trucks, to the servo controller and to the motor servo. So that's basically what happens, and that's basically what you need to know to understand later on when you see the trucks in action. Yeah, that's all.
Thank you. Then we're going to have Sebastian Pardo talk about the motion capturing system.
Yeah. So we use a motion capturing system as mentioned, which from the company Qualisys.
This is basically, it's 4 infrared cameras which look at the scene from different positions. And then we place on the objects, you can see them here, these little balls, they're reflective markers. So they reflect infrared light very well. So basically what the camera sees is little dots. And because we calibrate the system and there's all kind of nice algorithms, they match this dots and they can recalculate the 3D position. At the moment we use a test setup with 4 cameras. KTH is about to buy a system with 12 cameras, if I'm not mistaken, which will arrive soon. And so we were sort of the first ones trying out the test setup provided by the company. And we use it sort of as the GPS simulation for our scenario. So we also try to like simulate the signals flows as if it were GPS. So that's how the lab looks like. You see there in the back we have the cameras, 2 other ones are standing behind the picture. And then you have all these objects, you have the quadricopter, you have the truck with the markers. And then that's actually the pictures, the processed pictures which the cameras send to the computer. So the cameras already look for the markers in the picture and they send the information of these markers. And it's a bit hard to see here, but you see sort of that you see these dots from different positions. And what happens then, it reconstructs the 3D positions of the markers, and from that you can define so-called rigid bodies. So that's fixed configuration of markers. So we showed the camera system once this truck and said these 3 markers, they are the truck, and the coordinate system of the truck lies somewhere here with respect to these markers, and the system finds it back. So there's nothing we programmed that's shipped with the system. Just had to use it. So a bit more in detail how this system is built up. As I mentioned, the cameras process already the markers, so they have a processor and they do all kind of smart stuff. This goes via a network to a computer which runs the Qualisys track manager, called short QTM. And this gives us the positions of the object, so we know like the orientation and the position of the truck, of the quadricopter, of the loads. And this is sent again via network to LabVIEW, and for LabVIEW they provide a nice client, which you can see there. It's basically this little box which gives us the positions and the orientations of the objects. So some words to how this behaves. This is a really, really nice sensor. It's really fast. We can have really high sampling frequencies. We have good accuracies. It doesn't disturb anything. It's super. But we have the problem that we have only 4 cameras, and this gave us a lot of challenges. That is, for instance, the most obvious one is that we have a small capturing volume, and it can happen that something like we operate really on the edge of the capturing volume, because otherwise we didn't have enough space. So it can happen that an object just leaves the capturing volume and we don't see it anymore. It can happen that we find, because we see only a part of the markers, and then it tries to somehow make sense of that, and that can happen that it suddenly finds the quadricopter flying upside down, which is not really good for any control if it just rotated 180 degrees. We have a lot of problems with marker occlusion, so that you either have you can imagine the quadricopter flying in front of the truck, so it's not seen by one camera, or also if the truck is like rotated in a certain position that the camera looks like this on the markers, then this marker will merge with that one. Yeah, and then we have this tracking algorithm which tries to find the rigid bodies that doesn't know anything about the system, so it's general purpose, which gives worse performance than if you could tell the system the truck is always standing on the floor, it's never upside down. You could do better estimations, but we cannot do this. We could in theory implement it, but we didn't have enough time to that. So this is all kinds of problems we had to deal with, which hopefully will just be gone if there's more cameras, because then you can have 3 cameras looking at the same object, and then if you occlude one camera, the other two see it, and everything is fine. That's to the motion capture system and now the trucks.
Yes. Yes, so I will talk about the trucks and how we managed to solve the problems with those. So basically what we had to do first was to set up some goals, what the trucks should be able to do for us to actually run the final presentation. It should be able to drive at a reference speed. It should be able to steer the truck to keep it on the road, to navigate in the road system, and also to arrive at a given destination. Be able to platoon with at least 2 trucks, avoid collision in the road network, which already talked about, the disturbing track, and communicate and interact with the rest of the processes. So basically we started off with a quite simple kinematic model, but we wanted to add some more dynamic to the system. So we added a backlash, a rate limiter, because the wheels can change instantly when we want them to. We added saturation and also a delay in the system. And we had to do some identification of these. So we made a step response on the velocity to get the time constant of the system. We also managed to send a triangle wave into the steering so that we could map how the backlash affected the steering and also map the input-output for the steering. We made some runs in constant speed so that we got mapping from an input to a certain velocity. We used sound recordings to determine the actual delay and rate of change in the system so that we could record a sound when we told the system to do something, and then we recorded the sound when the motor actually started doing something. And we could just look at the time delay between those two. And we also made a lookup table for mapping input-output, which we put in the model. And what did we use this for then? We used it with the identified parameters we used as a start, but then we moved on to tweak the model to fit it to the real trucks. Because in LabVIEW we could send the same signals to both the model and to the real trucks, so that we could make the model behave exactly as the real truck did. And when we thought that we were happy with this, we actually used the model to tune the PID parameters so that we could get a nice control about it before we actually moved it to the truck. And it was quite successful actually. And I also want to talk about how we implement the road system. So basically we take the road network on the floor and then we draw a truck around in the network, recording with mocap. And we took this data and took it into MATLAB, where we created waypoints along this road, with the feature that every waypoint has a local coordinate system, with the x-axis pointing towards the next waypoint in the system, so that we can basically prolong the distance between them and make the truck follow that line in between them. And we can also set the distance between waypoints and the deviation between different waypoints so that it fits our trucks actually. So the truck is basically following a straight line between 2 waypoints. And when it arrives at the waypoint it's aiming for, it changes it to the next waypoint, and so on and so on. So how did we do the control then? Well, this is a very simplified picture of the platooning regulation. So that the master truck, the truck in front, gets a speed limitation that it has to follow by the road. Basha will talk about that later. And it tries to regulate itself to keep this speed then. The slave truck, however, the second truck, actually receives the velocity of the first truck, the reference velocity, as a feed forward. So it keeps the basic distance between the 2 trucks. So you only make fine adjustments with the PID controller. And the steering then. We also use a feed forward for the steering, because when we passes over a waypoint, the road slightly changes direction, as you can see from the picture, and you get quite a large deviation from the actual road. And we wanted to correct this kind of fast before the PID actually has to set itself to turn the truck. So what we do is we feed forward the difference between the truck orientation and the road
orientation basically, so that the truck automatically sets towards the next waypoint, and then the PID does the rest to make fine adjustments. And we managed to get the road following down to about 5 centimeters plus and minus deviation from the road. And this was a requirement that we thought suited our solution, because we needed to load the truck later on. So this was the maximum deviation that we could really handle with the crane and so on, because then we're still on the road with trucks. And now I think Pasha will continue a bit more.
Yeah, I'll talk about the road network. So basically, the road network is composed of a series of road segments, and a road segment is similar to a road in the sense that you're able to drive on it. So every road segment is associated with properties. For instance, we have speed limits, and this is like something we need to have because the vehicle needs to slow down when it arrives to the crane, and it is allowed to go at a faster rate when it's not around the crane. We also have a property related to that only one truck fits in the lateral space of a road segment, as illustrated in the image. And this is also like some kind of simplified version of how our road network should look like. Different speeds, platooning trucks. Okay, so as in real life, we're faced with the need to express a destination, a street address, and basically what we have is that a street address is defined by a road segment number and a traveled road distance. And an example of a street number is, for instance, road segment 2 and road distance 3.4, and that's, for instance, over there. And if the trucks would come to that point, then they would stop or just pass by, depending on how we want it. So the vehicle is at its destination when the specified road segment and the specified traveled road distance equals to where we are on the road. So basically, the question is, what is a traveled road distance? Well, you can keep an eye on the image while I explain. It's basically the accumulated distance of the waypoint nearest the rear of the truck, with summation, it's summed with the interpolated distance that is between two consecutive waypoints, meaning the truck position. So by doing this along the way, we're able to find out where on the road the truck is, and in this scenario it's 5.4, and as I said earlier, if we had specified that road segment and 5.4 as a street address, then the car would simply stop there. So in order to arrive at a given destination, we need to have some kind of navigation information. What we use when we drive around in our road network is we use, for instance, road signs, and here we have some things that is similar, and we have a routing table. So in addition to being some kind of road abstraction, the road segment is also some kind of intelligent entity that's able to answer the question, which road segment should I embark on next in order to eventually arrive at my given destination. And here in this example, the truck is asking the road segment, should I take road segment 3 or 2 in order to eventually arrive at road segment number 5. So the answer is simply, so the question is simply answered by just asking the road. The vehicle needs to query the current road that it is on for which road segment it needs to go to, and in this situation, the truck is able to read the sign where it says, follow this road if your destination is road segment number 5, and this information is encoded in our routing table. So it knows where to go if it wants to go to road segment 5. So path planning is dynamic in this sense. There is no reason to know your entire journey in detail when disembarking your starting position, and this kind of path planning is very much rooted in reality, and because the decision making is decentralized in this fashion, we're able to change a route just on mid-journey if we wanted to, if there is a traffic jam, for instance. So if we look at this example, if you were to send a letter to somebody in Gothenburg from Stockholm, you wouldn't actually specify the address like that, because there would be no point in doing that. You would just write like this, because when the letter eventually arrives to Linköping and Jönköping, we have a routing hub that is able to redirect depending on where the destination is. And this is how our road network works. So a word on collision avoidance. So collision avoidance is handled internally and automatically by the road segment, and you're going to see an example of that later on during the demonstration, where we avoid the disturbing truck that Ari talked about. So this is done by, we have some kind of mechanism where a vehicle needs to request or to apply for the right to drive on the upcoming road. And in this example, we see that vehicle B is not allowed to go into road segment 1 because vehicle A is already on that road segment. So to sum it all up, if there is a pending road request from vehicle A on road segment 1, then vehicle B is given the wait signal. So as soon as vehicle A leaves the road segment that vehicle B wants to enter, vehicle B is given a go-ahead signal. And we have like a first come, first served basis for this, and it works fine. So before I end this, I would just like to talk about our state machine. Our state machine is basically how we interact with the rest of the systems, with the quadricopter and with the crane. And the platooning trucks adhere to the signals that are sent from the state machine, and you can think about the state machine as some kind of control at a higher abstraction level, as opposed to the PIDs that Joachim talked about, that are control at a much more lower abstraction level. And if we're just going to have a look at this example, we see that our state machine gets a platoon request from, for instance, it only gets a platoon request from the crane via TCP/IP, and what it does is it reacts to that by changing state and sends 2 new states to truck 1 and truck 2 and telling them to enter platooning mode, because we want them to platoon to the destination that is requested in the platoon request. And we also need to send a quadricopter request, because we're not allowed to move outside the crane area without a quadricopter above us. And basically this is how our state machine works, and if you're interested, I can explain when you see the demonstration. And this was basically all from me and Joachim, and I would like to hand over to Kai and Jens.
Yes, so me and Kai have been working on the crane. It's basically a smaller version of a big tower crane, usually used in construction. The main parts are the tower, the jib, and the trolley, and this hook that we use to pick up loads. The crane can move the hook in any direction by rotating the jib around the tower, or lower or rise the hook, or move the trolley. When we started the project, we had the purchase order with some requirements on the crane. The first one was that the crane should be able to move its loads to a given destination as quickly, accurately, and safely as possible. And the second one, the crane should be able to plan the trajectory of the loads with respect to other objects or obstacles in surrounding. For example, we need to avoid the trucks. We don't want to swing the loads into them. And last, the crane should be able to automatically attach and detach loads with distinct masses. So these loads looks like this. First, we plan to use the 3D printer, but the cost was way too expensive. So instead, we made loads by ourselves, and this one is made from a pet bottle and gingerbread jars. And on top of the load, you can see the mocap markers, which we determine the position of the load and also the orientation, so we know in which direction we should go into it with the hook, and then we lift it. The last year when they used the crane in the automatic control project, they used the PID, or delay controller. They call it a delay controller. But what we wanted to do is to use model predictive control, And one big difference between these two strategies is that to use model predictive control, you need a model. Kai will later explain how the model predictive control works. But yeah, so the crane is a highly non-linear system, and the model we use is linear. And we got it from a master thesis, and we have 10 states that we estimate with a simple gamma filter. And in the last in the project they had last year, they constructed like pre-compensation for the non-linearities. So basically we use a linear model and compensate for non-linearities. And examples of these non-linearities could be dead zones and backslash. Yes, okay.
Yeah, as Jens mentioned, we use a model predictive control. Yeah, since we don't know how familiar you are with this, I will give a brief introduction. What is done with a model predictive control is that it's used for sample systems mostly, and for every sample it runs optimization, which means for predefined horizon or predefined samples in advance, it optimizes the trajectory, as you see it, for example, in here, and the first output action is then applied to the system, and the whole thing repeats with another optimization, and the first control action is taken for the next sample, and so on. Yeah, the important thing therefore is to have very precise models, since for the optimization we use this model to predict its behavior and its trajectory. Yeah, that's why I really needed a very precise model. And in the end, even though we use a completely linear model for our nonlinear system, we got a quite nice behavior. So that means we also defined the cost values or the cost function for the optimization problem. And we could also define constraints for the system. So that enables us to run the crane around the working point at the borders of the working region or the working range, which is, for example, if the truck is quite far away from the tower train, from the crane, and it needs to be loaded. And also the MPC enables that we have quite fast position changes, since for a long enough horizon we get the more or less optimal trajectory for this position change, and therefore we can just give it more or less a step and references, and we don't need to define the complete trajectory, since the MPC takes care about that. Yeah, then we also need to do some other things, like getting the position of the trailer to know where to put the load. And the problem there with is that we don't measure the position of the trailer, but only the position of the truck. So what we used is a discretized method from the so-called kinematic car. And the only problem with it is that we don't know the initial position of the trailer. So that means we need to make a guess and then wait until it's converged to the actual position. And here in these two figures you see a simulation we did for two different trajectories of the truck, where the red line is the truck trajectory, and the blue and purple ones are the trajectory or the simulated trajectories for the trailer with different initial positions. Yeah, for these different trajectories, and as you see, after 1 or 2 meters, it almost converges, and what we do then is just to have assume that the trailer is in straight line with the truck in the initial position, and yeah, with this method we can compute the trolley, the trailer position quite good, and we can place it then directly on a given position on the trailer. And yeah, the highest level of our program runs a state machine, which coordinates the truck, the crane, and also takes care about messaging, like giving the request that the trucks are needed and the request for the trucks to go to specific positions. And also, yeah, turn the control off and on, since otherwise the crane makes yeah, some unnice noises. That's basically from. Okay, now we have also some future work is to do, like improving the model, since we use the completely linear model in the moment. But what can be done is make a more precise non-linear model. Also improve the control to use the updated control instead of a linear control, or even a bit more advanced, a non-linear modulative control. Then we use attach-detach mechanism without an actuator, but this can be changed also with a magnetic actuator or a grabber. Safety could be improved, since what we are doing in the moment, we're just moving the load to a height where we know there's no obstacle in the way to then the position change and place it. So constraints like some other obstacles on the way could be taken into account as well. And of course, many other things. Yeah, and now Christina and Frederick will continue with quadricopters.
So here is our quadricopter. You can see it there as well. And we use the quadricopter platform, and we started off by building a quadricopter from the start. We had to do some soldering and so. And this one uses an open source software called Arduino, and it has onboard stabilizing PID controllers. So we have not been working anything with the stabilizing controllers. We work with position controlling. And to communicate with this, we use wireless T-mode Polulu connection that Bashar talked about before. So we emulate RC or radio signals. And here is a model of the quadricopter. It has 6 degrees of freedom. So it's the position in X, Y, and Z, and also the angles, roll, pitch, and yaw. And we control it with 4 different inputs. It's the thrust, and then the angles again, pitch, roll, and yaw. And we have some requirements on the quadricopter to be able to fulfill the final scenario that Ari talked about before. So first of all, it needs to be able to be stable at a given height and a given position. And then we need to be able to follow a trajectory, since we will follow the trucks around. We also need to avoid obstacles, and the obstacle we have is the crane. So we have a function for that Fredrik will talk about later, and we also need to be able to take off and land autonomously. And to do this, we have a few control strategies. First of all, we use PID controllers. We have one for altitude, and one for X position, Y position, and then one for yaw. We do some trajectory planning, because this was the avoid crane function. So Fredrik will talk about that as well. But we do some trajectory planning. And we have fixed procedures for takeoff and landing. So the takeoff is, first we arm the motors, and we do that by send a specific servo signal for a few seconds, and then the motors can start. And then we quickly increase the throttle so it goes up a bit. And then we switch on the PID controller on altitude. And then it checks if it is at the reference height and before it goes and find the quadricopter. So if it is at the reference height, it can go and find the truck and follow it. To land, it first goes to the XY position of the landing pad, and then it checks if it is stable above the landing pad, and if it is that, it decreases the throttle and land. And during these procedures, the other PID controllers for pitch, roll and yaw are active. And now Fredrik will talk about our safety measures.
Yeah. So this quadricopter model we use, the quadricopter, it's a quite powerful quadricopter, and they usually fly it outside. So we need some systems to take care of, to handle safety requirements. Because if we lose it from the motion capture system, then we can get some irate behavior. So if we just lose the quadricopter momentaneously, like for short periods of time, then we estimate its position from the previous data points, just to have something to keep working with. But if we are lost for an extended amount of time, we pick a new reference which is towards the middle of the room, where we know that the motion capture has vision, and then the quadricopter will take that position and act on that reference and act on that. So we will hopefully move towards the room and then get the motion capture again. And then when we are within motion capturing range, we can pick the regular reference again, which would be following the truck. And we also have to avoid certain areas in the room around the crane. So what we do is we define an area which we can't fly inside, a circle around the crane. And if our current reference goes inside this area, we pick a new reference just on the edge of the circle and follow that while the truck is running inside that area. And when it's outside, we can follow the truck again. And just in case something bad is about to happen, we can take control manually via gamepad. So then we just have the current throttle, keep that, but we take over the control and can do whatever we want. This is a run through about from takeoff to a landing, some plots to show the performance. This is the plot for the yaw, where we keep the same yaw angle at all times. We face it 90 degrees rotation. This is the X plot, so we move around in the room following the truck, and you see some spikes in the blue reference. This is what happens when it goes outside motion capture range, so it goes back towards the middle. And here we also have the this is when the quadricopter comes around, and then this is where the crane is, so then we get this little bulge, and then we find the truck again and follow it. Yep, and here's the altitude. So same thing here, when we lose the motion capture system, we pick a new reference which is slightly lower, so we can try to lower the quadricopter and get back into motion capture range. And this is what we have to say. Ari will go back and finish this off.
Yeah. So you've heard pretty much what we did in big steps, at least. So how did it go in the course? I want to talk about that for like a minute or something. Well, in project management, you have these three constraints in a triangle: time, budget, and quality. Now, we didn't really have a budget other than our time. Like we had some fixed time on the overall project, but then our budget is pretty much just our resources. So we are here with a finished system. So with regards to time, we're good. budget. We didn't overwork anyone, and it was quite a good workload over the whole course. So in that sense, it was a success as well. And the quality, you'll see that later. But we're quite confident in the system. So what's left in the course for us to finish this course? There's this final presentation and the demo that you're going to see in a few minutes. And then we have to hand in a final report and the final documentation package that I talked about briefly earlier. That is for the 7th of January. But yeah, so after that, the course is done. This is maybe interesting for those interested in taking the course at a later time, if there are any SCR students here on the first year. So, something not working here? Okay. So, at the beginning we had we had a mandatory team building exercise, and we spelled out the course code. So again, for the students that are in the first year and want to take this course, the course code is EL2421. Thank you for being here. I don't think we have here and now, but if you follow us to the lab and are present at the demonstration, we can answer any questions there. So, thanks.
Well, if you don't know where the lab is, you should just follow the crowd.
Yeah.